Hello everyone, this is Convexity and Jensen's Inequality. So, a little bit of a note. So this channel is about math and programming and maybe kind of general philosophy later on. But, one thing I wanted to get out of the way is that you should expect there to be mistakes in these videos. I'm going to say things occasionally that aren't correct, or, maybe I could have said it better a different way, whatever. So, I'm saying this so that I don't stress out about tiny little mistakes in my presentation. Alright. So, convexity. So, convexity is important just because it comes up a lot, and it always comes up in ways that make your life easier. So, typically you have some problem, and usually what happens is you have some function, and what you can prove is that, well, if this function is convex, or if this shape is convex, then my life becomes a lot easier. Then the problem becomes really trivial and easy to solve. And if it's not convex, then you're in trouble. By the way, new convention that I'm going to try to stick to is that if you see some letters, or if you see a word that's a different color than the paragraph it's in, then it's a reserved term. So convex means something specific. A shape is convex if it contains the straight line segment connecting any two of its points. So this shape, this triangle, is convex because I take two of its points. Let me make sure that I'm recording on the correct microphone. Yes, I am. Go away. Anyway, this triangle is convex. This weird banana shape is not convex because I can take 2 points, draw the straight line between them, and it leaves the shape. There's no 2 points in this triangle where if I draw the straight line between them, it leaves the triangle. So, and in this video, when I draw a shape, I mean both the boundary and the interior. Alright, so this notation I invented, it's not really much of an invention, but little gamma of source, destination, and time. So source and destination are points. Time is a number between 0 and 1. And it's equal to 1 minus t times source plus t times destination. And it just means the straight line segment going from source to destination. So you plug in 0 in this equation, t equals 0, you get sigma. T equals 1, you get delta. Otherwise, you get a point between sigma and delta. So this line segment is the set of all points gamma of sigma, delta, and t, where t ranges between 0 and 1 inclusive. And then this set is called big gamma of sigma and delta. A set is, set should be a reserved term. Oh well. A set is, so really the reason I'm saying this is, what's sort of the minimal structure you need in order for this idea of convexity to make sense? So this is how we define a straight line path, but in order to define it, you need the ability to multiply points by scalars, and then you also need the ability to add points together. So you need to be able to take linear combinations. Specifically, you need convex combinations. So Rn, I use Rn because it has all those properties, and most spaces can be embedded in Rn. So a set S subset Rn is convex if for all, that's what this upside down A means, sigma and delta, this means element of, so for all sigma and delta that are elements of S, then the straight line segment from sigma to delta is also contained as a subset of S. So here is sigma, here is delta, here is the straight line segment between sigma and delta, and what I'm showing in this graph, so this big round shape is S, what I'm showing in this graph is that actually, if you know that a shape is convex, then what you can do is construct these things called convex holes. H-U-L-L, sorry, I can't say that word. Convex holes in the shape. So you take sigma and delta, and then you take a third point in the shape, call it alpha. Well, by convexity, the shape contains the straight line from sigma to alpha. By convexity, the shape contains the straight line from delta to alpha, and then, well, you pick a point x here that's on the straight line between sigma and delta, well, by convexity, S also contains this, S also contains this orange line, which is from the straight line from x to alpha. So, you just repeat this for every x on this line, and you can fill in the whole triangle. And similarly, you take beta, and you repeat the construction using every point in the triangle, and you can get a quadrilateral. You could get any polygon that is, has a finite number of points. And so, this is called the convex hull. So, equivalently, we went from, you have 2 points and you can construct the straight line between them. Well, now if we say a shape is convex if it contains the convex hull of any finite subset of its points, well, if you just take the convex hull of 2 points, then you recover the original definition, and from the original definition you can recover this definition, so therefore they are equivalent. And then sometimes you hear the word simplex. This is important, and they're not quite the same thing, but every simplex is the convex hull of something, but sometimes convex hulls aren't simplices. So convex hull of 1 point, that's the point. 2 points, that gives you a line segment. 3 points, that gives you a triangle. 4 points, that's a tetrahedron. If all points are coplanar, that's a quadrilateral, so that's what we have up here. So 4 coplanar points, you take the convex hull, and that's a quadrilateral. If B was out of the page, then this would be a tetrahedron. So you can imagine. Maybe you can visualize this as a tetrahedron. That might be easier. Notice that in each of these cases, the dimension of the object is the number of points minus 1. So point is 0-dimensional, segment is 1-dimensional, triangle is 2-dimensional, tetrahedron is 3-dimensional, but point is made out of 1 point, segment's made out of 2 points, triangle, that's a 2-dimensional object made out of 3 points, tetrahedron, 3-dimensional object made out of 4 points. So there's some interplay between the number of points and the dimensionality of the object. So the reason this is important is because, I'll circle back to that. Anyway, observation is that you take 2 points, the convex hull between them also encodes all probability distributions. So heads and tails, you pretend those are points, you take the straight line path from head to tails, lo and behold, every point on the line corresponds to a probability distribution on heads and tails. And moreover, every probability distribution on heads and tails corresponds uniquely to one of the points. And so this one, ht 3/4, you plug that into the original equation, you get 3/4 t plus 1/4 h. This also holds true for higher dimensions, but there's a little caveat, which is that you need the dimension of the simplex to match what it's supposed to be. So you can't, for instance, have so up here we have, for instance, the tetrahedron in 2 dimensions. That's not going to work. Because a tetrahedron, that's a 4 simplex that lies in 3 dimensions, and we're projecting it to 2 dimensions here, so we're not going to get unique representation of, meaning every point is going to correspond to multiple possible probability distributions if you have the simplex with the proper number of dimensions. So 4 simplex has 3 dimensions, so on. So n points lies in a shape of n minus 1 dimensions. That's how you can guarantee unique representation. Like, for instance, if you put a third point on this line, so let's say that you have a coin with 3 outcomes. You can see how if you take convex combinations of these 3 points, then you don't get unique representation, meaning you have 2 different algebraic expressions that correspond to the same point. And that's not ideal. So you want there to be a 1-to-1 correspondence between the points in the shape and probability distributions on the vertices in the shape. So here, this is showing just how you go from, so right here, I think it's pretty obvious how if you have 2 points, it's pretty, let me make sure I'm recording with the right microphone. I have a habit, yes I am. I have a habit of doing a recording and then discover that it was selected the wrong microphone and so it didn't record any audio. Anyway, so this also holds true for higher dimensions, meaning the number of probability or the set of probability distributions on a finite number of outcomes is a convex space. So, for example, if your number of outcomes was the alphabet, so you want to have a probability distribution on the letters. The letters don't have any geometry to them, like the set of letters that doesn't have any, that's not like a vector space or something like that. However, the probability distribution on 26 letters, that is a well-defined shape. That's so 26 letters, that is a 26-pointed simplex, which lies in 25-dimensional space. And that has a well-defined geometric representation. So that's kind of the point I want to get across here, is that if you have probability distribution on a finite number of outcomes, that has a really well-defined geometric representation as a convex shape. So this is showing an example. So we have point A, point B, the straight line between them is all probability distributions on A and B, and then this is showing how, well, you take some random point in the simplex. So you take this point P, you draw the straight line from C down to the line from A to B, call that point X, and then, well, you know, so say X is gamma of A, B, and 0.2, P is halfway between them, I decided, and then so, well, P is half of X plus half of C, you plug in the expression for X, you get 4/5 A plus 1/5 B, you do some simplification, and this point P corresponds to 4/10 A plus 1/10 B plus 5/10 C. Notice that 4/10 plus 1/10 plus 5/10 is equal to 1. So indeed, this is a probability distribution on 3 points. Right? Fair enough? That makes sense? And so every point in an n-simplex delta n, that's a reserved notation, corresponds to a unique probability distribution on n outcomes, and likewise. So again, the simplex is the convex hull on n points that lies in the proper number of dimensions. Okay. So, if we have a real valued function on a probability distribution like, say, uncertainty, I did another video on uncertainty if you want to know more about this function. This is part of actually the information theory series. That's hard to say. Anyway, now if we have a real valued function on a probability distribution like, say, entropy or uncertainty, whatever the hell you want to call it, then we can view it as a function on delta n. So, probability, that doesn't really have a well-defined geometric representation, that's kind of abstract, but now h of delta n to r, well, now h has a domain with a really well-defined geometric representation, and we can use facts about geometry to tell us things about probability. That's really the key here. And we can use things about probability to tell us things about geometry. That's what it is. So we're going to circle back to this entropy because what's important is Jensen's inequality. So a function is convex if the region above its graph is convex. So convex and graph, those are reserved terms. Graph just means the set of pairs x and f of x, where x ranges in the domain of f. So the graph is the set of points on this blue curve, and if f is some function. So again, convex functions, so you take 2 points in the region above its graph, they're going to be contained in the region above its graph. So a function that isn't convex, for instance, I don't have the drawing pad. Here, you can scroll down actually. Don't look. this function is not convex. So you take a point above the graph, another point above the graph, and you connect them and you leave the region above the graph. So that function is not convex. Anyway, convex functions have the property that if we draw convex holes using as vertices points on the graph, then the hole will always be contained in the region above, I should have said the region above or on the graph. This fact is called Jensen's inequality. So here is an example with 4 points on the graph. We drew the convex hole of 4 points on the graph. It lies in the region on or above the graph. So I labeled these T1 and f of T1. This is T2 and f of T2, T3, f of T3, T4, f of T4. The pink region is all convex combinations, so all probability distributions on these 4 points. Not quite, because we're not in the right number of dimensions. You get the idea. Because, whatever. You know what I mean. The points in the pink region are all above or on the blue line. That's the point. Algebraically, so this is f of T1, T2, T3, T4, or f of gamma of T1, T2, T3, T4. Gamma of T1, T2, T3, T4, that is this interval. So it's the set, it's the convex hole of T1, T2, T3, and T4. Of course, that's just the convex hole of T1 and T4, since T2 and T3 are in the convex hole, so really adding them doesn't do anything. But it's saying that f applied to this interval, that'll give us the part of the curve that's here. And the convex hole of these points always lies strictly above or on the blue region. So, right, we established the pink region is the convex hole of these points, and all Jensen's inequality is saying is that the blue curve is always on or below, or the pink region is always on or above the blue region, the blue curve. Pick some convex combination. Convex combination means probability distribution. Pi 1 T1 plus pi 2 T2 plus pi 3 T3 plus pi 4 T4. These are the rules for probability distributions, so all of the probabilities have to be between 0 and 1, and they have to add to 1. Then f of pi 1 T1 plus blah 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 pi 4 T4. So that's saying f of whatever. This is some convex combination of T1, T2, T3, and T4. It lies here. You take f of it, you plot here, and you take that same convex combination of these control points, and you're going to wind up somewhere in this region that is above the curve. That's what this is saying. So this is in particular just taking the y value. So that is, you pick a point x, y in the pink region, then f of x is going to be less than or equal to y. So here's x, y in the pink region, drop it down, x and f of x. X, again, is some convex combination of T1, T2, T3, and T4, right? X is a convex combination of T1, T2, and T3, and T4. Y is a convex combination of f of T1, f of T2, f of T3, and f of T4. And we get f of x is less than or equal to y. Right. The opposite inequality will hold if f is concave, meaning the region below the curve is convex. So here we have, ignore those are from earlier. Here, so concave means the region below the curve is convex. Here we have 3 control points and a point in the simplex. You draw the straight line up from the point to the point on the curve, and you have y is less than or equal to f of x. That's literally all Jensen's inequality is. Well, not quite, because Jensen's inequality works in a little bit more generality than this, but that's all the idea is. Jensen's inequality is just recognizing that you do this construction, and it's always going to be the case that the numbers that the y values in the convex hull are going to be whatever. The y value in the convex hull is going to be greater than or equal to the y value on the curve. That's literally all it means. All right. That's all for today. Please join me in the next video. Thank you.